A pharmacist in an isolated clinic scans a blister pack of antibiotics, checking for anomalies in a supply chain without reliable internet access. The software processes the image entirely on the device, rendering an immediate verdict, a bright red critical risk warning. To be clear, this system does not replace a mass spectrometer. It acts as a visual triage layer, analyzing batch codes, expiry dates, and structural inconsistencies in the packaging. Standard verification tools rely on cloud APIs, which fail exactly where counterfeit risks are highest. An isolated environment requires the inference engine to run entirely on local hardware. Issuing a definitive health warning without network validation demands absolute certainty, both in the model analyzing the package and the integrity of the device executing the code. The architecture solving this offline problem relies on three distinct pillars. First, the logic layer. A Gemma 4 E2B vision language model analyzes the photographic evidence natively. Second, the execution layer. Google's LightRT engine manages the hardware-level matrix math. Third, the security layer. An ED 25519 digital signature locks the resulting analysis into an immutable record. Moving a neural network to a phone solves the connectivity problem, but securing the resulting data against local manipulation is what makes Edge AI viable for medical logistics. The model evaluates the package against a strict risk taxonomy. A score under 30 registers as low risk, confirming the packaging aligns with authentic variants. Scores climbing towards 65 hit the moderate threshold, flagging minor anomalies that require manual review. A high-risk score indicates multiple structural red flags, while a critical rating above 85 points to direct evidence of counterfeiting or a match with a known bad batch. The process begins when the camera frames the package. The application captures the image, locks the focus on the batch code, and extracts exact GPS coordinates. The internal Cactus service bundles this data. It combines the photographic evidence with a strict task description and the system prompt. But passing a high-resolution image into a mobile vision model creates an immediate memory bottleneck. To prevent a crash, the application enforces a strict 560 vision token budget constraint. This exact allocation forces the engine to compress the visual data into a fixed grade, preventing the mobile device from exhausting its memory when analyzing complex, text-heavy blister packs. Alongside this memory limit, the system locks the model's temperature at 0.1. By restricting both the token space and the creative variance, the architecture forces the neural network to output repeatable, structured JSON logic instead of conversational prose. Getting the image into the local engine introduces another technical barrier. Standard image compression destroys the precise pixel data needed to read microscopic batch codes. The pipeline circumvents standard JPEG compression entirely. It routes the raw, uncompressed data directly to the inference engine as raw image bytes. That engine is LightRT LM, embedded natively within the Android operating system. Rather than relying on the device's main processor, the engine defaults to hardware-accelerated matrix math, executing directly on the native Adreno or Mali GPU cores. Mobile hardware is highly fragmented. If the system detects an incompatible GPU driver, it triggers an automated fallback protocol. The data path reroutes to the standard CPU, extending inference time from seconds to 2 minutes. As the engine calculates the output, it uses a message callback function to stream the results sequentially back to the user interface. A parsing module catches these streamed tokens in real time, assembling them into the final JSON payload. Preserving OCR fidelity without cloud compute requires this direct hardware execution. The model must process the raw pixels efficiently, or the user experience collapses. The inference is complete, but storing the result creates a new vulnerability. Local SQLite databases on mobile devices are easily accessible and highly vulnerable to offline tampering. To solve this, the application initializes a signing service that generates a unique asymmetric key pair the very first time the app launches. These base64 encoded keys are locked inside the platform-native encryption of the device's secure storage. The moment the JSON payload is finalized, the system constructs a cryptographic proof. It merges the exact timestamp, the extracted batch code, the risk score, and the GPS location into a single unified block of data. It applies a SHA-256 hashing algorithm to this unified block, distilling the scan parameters into a fixed-length string. The device then uses its private ED2519 key to mathematically sign that hash. Finally, the internal database writes the complete package, the inference result, public key, and unforgettable signature, into a local SQLite table. It applies a flag marking the record as synced equals 0, designating it as a pending offline asset. The result is an airtight chain of custody. A highly vulnerable local database is transformed into an immutable ledger of evidence, locked and ready for transmission. The isolated evidence sits dormant until the device finally reconnects to a Wi-Fi or cellular network. A background sync service detects the network state and queries the database for all records flagged as pending. It gathers the collected evidence into a batched HTTPS post payload and transmits it to a central backend server. The server extracts the public key from the payload and mathematically authenticates the ED25519 signature to guarantee the record was not altered while the device was offline. Once verified, the server commits the data to its own database, instantly updating a global dashboard tracking counterfeit risks across regions. Shrinking a language model to fit on a phone solves a processing problem. Deploying it safely into the physical world requires an architecture that binds that local intelligence to an immutable, cryptographically secured data pipeline.